Dr. T.V. Geeta, Professor, Department of Computer Science, College of Engineering, Guindy, Anna University. Her special interest, Artificial Intelligence and Natural Language. She has published more than 143 articles in national and international journals. She has guided around 7 PhD students. She has got Young Scientist Award from Government of Tamil Nadu in the year 2000, Chief Minister's Special Mention Award in the year 2002, and Woman of Excellence by Rotary Club in the year 2003.
Welcome to the UGC lecture series. In this lecture, we are going to talk about how the issues regarding recovery and atomicity, in the sense that we are going to talk about how recovery will affect atomicity and what we should do about it. We are also going to talk about storage structures, more in detail about storage structures. So, we discuss the issues in recovery and atomicity. We describe the different types of physical storage media. We have had a glimpse of it in the previous lecture. Then we talk about the different aspects of storage hierarchy, and then we look at buffering for how we use buffering for recovery purposes. So, last time we had looked at buffering management, but we looked at how buffers are managed, but here we are looking at it from the recovery viewpoint. So, first let us look at recovery and atomicity. So, modifying the database without ensuring that the transaction will commit, that is it will actually finish completely, may leave the database in an inconsistent state. We have seen this a little bit before in lectures that we had before. So, for example, you consider a transaction Ti that transfers rupees 5,000 from account A to account B. Now, what will happen if the transaction is not committed? 5,000 will be taken from account A, but it will not be reflected in account B, and this is what is typically called as an inconsistency. So, goal is either to perform all the database modifications made by the transaction Ti or none at all. So, several output operation may be required for completing the transaction Ti. So, output to A and B and so on. A failure may occur after one of these modifications have been made, but before all of them are made. So, that is the key issue there. This is atomicity, the definition of atomicity. So, to ensure atomicity despite failures, what we will have to do is we will first output information describing the modifications, what are the modifications that has be done by this transaction to a stable storage without modifying the database itself. We do not do the modification to the database, but we just say that these are the modifications actually going to happen. So, there are two approaches that we have already studied. One is called log based recovery and the other is called shadow paging, which we have already discussed. So, we initially assume that the transaction runs serially, that is one after the other. Now, we will look a little bit again into checkpoints. So, the problems in recovery procedure have been discussed earlier, that is you have to search the entire log and that is very time consuming, and we must unnecessarily redo transaction which have already been committed and the output have been put into the database. So, you have to streamline the recovery procedure by periodically performing checkpointing. So, what we do during checkpoint, we output all log records currently in main memory onto the stable storage. Now, we are talking more about the storage management, how from main memory we have to put it into stable memory. Then all the modified buffer blocks that have been in main memory have to be written to the disk and write a log record checkpoint onto the stable memory. So, all these three operations you have to do during the checkpoint. We have discussed checkpoint, we are looking at what all have to be put into the stable storage. So, three things you have to put to the stable storage or the physical disk or whatever we call it. One is the log records that are currently residing in main memory, that you have to put, then that is log, what are the operations you have done. All the modified buffer block, because of the transaction some buffer blocks may be modified. So, all those buffer blocks you have to put it onto the disk or write it onto the disk, and a log record saying that this checkpoint is over, that also you have to put it into the stable storage. So, during recovery we need to consider only the most recent transaction Ti that started before the checkpoint and transaction that started after the transaction Ti. So, you take the most recent transaction Ti that started before the checkpoint and transaction that started after Ti. So, scan backwards from the end of the log to find the most recent checkpoint record. Remember, previously we discussed how this checkpoint also has to be stored, and continue scanning backwards till you come across a point where the transaction Ti has been encountered, start transaction has been encountered. You need to consider only that part of the log record following above the start record. Earlier part of the log can be ignored completely during recovery and can be erased whenever desired, because all that has already been committed. So, what we are doing, we are going backwards until start Ti. For all transactions starting from Ti or later with no Ti commit, that is none of the transactions have committed, you have to undo all the transaction. It is only done in the case of immediate modification. Scanning forward from the lag, for all transactions starting from Ti or later with Ti commit, execute, redo. So, you have to redo and undo. So, let us take an example. You have the transaction T1, you have the transaction, this is the TC, you have T2, T3, T4 and you have here. So, T1 can be ignored, updates already has been output to the stable storage, T2 and T3 has to be redone and T4 has to be completely undone. So, this is the system failure point and this is the checkpoint point. This is the issue of checkpointing. Now, let us look at the recovery with concurrent transaction. What happens when concurrent transaction happen? So, we modify the log based recovery scheme to allow multiple transactions to execute concurrently. If you did not have, in the previous case we looked at when the transactions were executed serially, but this is not practicable. So, we have to look at transactions that are executed concurrently. So, all transactions will share a single disk buffer and a single log. So, a buffer block can have data items that have been updated by more than one transaction. So, that is possible. So, we assume concurrency control using strict two-phase locking, that is the updates of uncommitted transactions should not be visible to other transactions. Remember atomicity, this transaction should see only the output of the other transaction. So, if you want to perform undo, if T1 updates A, then T2 updates A and commits and finally T1 has to abort. So, what will happen? Then T2 will be completely wrong. So, with concurrent transaction, logging is done as already described. Log records of different transaction may be interspersed in the log and the checkpointing technique and the actions taken recovery have to be changed, because now we are talking about several transactions which may arrive when a checkpoint is performed. So, checkpoints are performed as before, except that the checkpointing log record is now of the form checkpoint L, where L is the list of transactions which arrive at the time of the checkpoint. We assume, however, we make one assumption, we assume no updates are in progress while the checkpoint is carried out. You can relax this later, but as of now we will assume that. So, when the system recovers from the crash, it first does the following. What it does? It initializes the undo and redo list to empty. Then it will scan the log backward from the end, stopping when the first checkpoint L record is found. For each record found during the backward scan, if the record is Ti commit, add Ti to the redo list. If the record is Ti start, then if Ti is not in the redo list, then you have to add Ti to the undo list. This is the basic thing. So, which are the transactions that has to be redone, which are the transactions that has to be undone. Okay, this is what we are trying to talk about. Remember the difference between undone and undone means you have to start the transaction all over again, including getting what it needs and all the resources it needs and all that. Redo means some operation has to be redone. So, for every transaction in that L, that is a list of transactions that started, if Ti is not in the redo list and add it to the redo list. At this point, undo list consists of incomplete transaction which must be undone and redo transaction consists of finished transaction that must be redone. So, this is what happens. Now, recovery now continues as follows. Again you scan log backwards from the most recent stopping when Ti start records have been encountered for every Ti in the undo list. So, you keep scanning backwards till you reach a Ti start for every transaction, that is, now before we had only one transaction, now we have concurrent. So, all the transactions that are there in the undo list. During the scan you perform undo for each log record that belongs to the transaction in the undo list. So, locate the most recent checkpoint L records and then you scan forwards from the checkpoint L. The same process we followed for the sequential. There we had only one transaction, here we are talking about concurrent transaction. So, you scan forward from checkpoint L and record till the end of the log, and then during the scan what you do? You perform redo for each log record that belongs to a transaction in the redo list. So, go over the steps of the recovery algorithm on the following log. So, what you do here is, now this is T0 start, then this is T0 some operation you do and you have T0 commit, and then you have T1 start and then T1 some B, T2 start, then you have T2C some T2 again is doing checkpoint. Now, at this point checkpoint is T1 T2, checkpoint is T1 T2 because here you have a commit and then you have a start here and a start here which has not been committed. So, T1 and T2 comes into checkpoint, then you have T3 start and so on and so forth. So, this is a simple example of how the recovery algorithm works. Basically, we have spoken up to now about recovery and atomicity in for sequential transaction as well as concurrent transaction. In concurrent transaction, all the operations of that particular transaction which may be interleaved are carried out. The checkpoint is done in the same way. You have a set of redos and a set of undos. So, that is the same thing. So, the transaction that has been done and so on. Now, we talk about storage. Now, let us go a little more in detail about storage. So, there are major classifications which we have already discussed a little bit. We can differentiate storage into two: volatile storage, contents of main memory, which are usually lost when there is a power failure or system crash, and non-volatile storage, which consists of when even the power is switched off, it will be there, and includes secondary as well as tertiary memory as well as battery operated backed up main memory. So, classification of physical storage media, you can classified based on different things. One is the speed with which data can be accessed, this is very important, and also the cost per unit of data, okay, and also the reliability. So, there are three parameters: speed, cost and reliability. Reliability means data loss and power failure or system crash, and physical failure of the storage device itself. Sometimes it need not be because of power shortage and all, power failure, it may be because of the physical failure of the storage. So, all these parameters will decide on which storage media is selected. So, now one of the physical storage media is cache, which is the fastest and most costly form of storage, okay, and it is volatile and it is managed by the computer system hardware. So, it is the fastest and it is volatile, but it is costly because the speed is the main criterion here. Then we have the main memory. So, cache, after cache you have the main memory. So, you have fast access, and you can generally it is too small to store the entire database, that is why you need a physical storage, and capacities go up to a few gigabytes, and capacities have gone up, and the per byte cost has also decreased steadily and rapidly. So, main memory being an issue, it is still an issue, but the intensity or the thing of the issue has decreased because the memory the size of the main memory has increased tremendously, and the cost per data unit, which was one of the parameters, has decreased and the speed has increased. So, all these makes main memory very important databases can even be maintained completely in the main memory, though that has not yet come, that is possible as we go along. And flash memory is another one. This is where the data survives power failure. Data can be written to a location only once, but location can be erased and returned to again. So, it can only problem is it can only support a limited number of write and erase cycles. You cannot keep on writing and erasing, then there will be corruption and you cannot use the flash drive. Erasing of memory has to be done to an entire bank. You cannot erase certain portions, you cannot do, and reads are roughly as fast as main memory, but comparatively writes are slower. Okay. So, that is another issue, whether the read operation or the write operation is slow or fast and erase is completely more slower. So, this is another type of memory. So, we have spoken about cache memory, we have spoken about main memory, we have spoken about flash memory. Okay. So, there is another type of flash called NOR flash, and here what happens is fast reads, very slow erase, and lower capacity. So, the very important things you can store there, and it is basically used to store program code in many embedded devices, because there the size is very small, and it is only a read operation, basically you program it and you read it. And then you have what is called a NAND flash. This is page at a time read write and in multiple page arrays. It is high capacity. It is widely used especially in portable devices like your laptop and so on. So, up to this point we have discussed about certain types of physical storages. Before we started, before that we talked about recovery and atomicity, the issues involved in that, and what is checkpointing and what happens when you write into the physical device and so on, physical storage and so on. And then we looked at different storage devices and what are the parameters that you use to judge when to use what storage devices, which itself is a major issue. So, there we looked at some, we will be looking at some more physical storage media after the break. So, now let us take a small break. Welcome back after the break. So, before the break we spoke about two things, one was the recovery and atomicity issues in memory management of the data files, and then we spoke about when it has to be stored into the physical device and things like that, physical storage, sorry, and then we spoke about certain physical storage media available. So, we spoke about some of them. The main the volatile we had finished. Now, let us look at some of the non-volatile. Non-volatile also was there, flash memory. So, now let us look at the another important aspect as far as database management is concerned. So, let us look at physical storage media, in which first we are going to look at magnetic disk. Magnetic disk is a very important physical media, because many of the operations are decided by how this is managed, the disk access, and disk access is very crucial part of database management system. So, data here is stored. So, we will go a little more in detail about how magnetic disk works. So, data is stored on spinning disk and can be read and written magnetically. It is a primary medium that is used for long term storage of data, and it typically stores the entire database. This is the first time we have come across a database, discussed a database that stores the entire database, and data must be moved from disk to main memory for access. You do not access it from the disk, and written back for storage. So, basically this disk is from where you take data, put it in the main memory, buffer of the main memory, use it for all the processing. After the operation is done, during a commit, it is written back to the physical the storage. So, it is a direct access. So, it is possible to read data on disk in any order, unlike magnetic tape where it has to be read sequentially, and it is non-volatile, that it survives power failures and system crashes, and disk failure can destroy data, but it is very rare that the complete disk fails, but it does happen. So, it is advisable for for database managers to store and have a redundant disk where you store the data, at least up to the point. So, this is very important, especially in today's world where a lot of databases are operating online for a lot of operations, and everything has become electronic operations. Another type of so that was the magnetic disk. Another type of very important storage is the optical storage. Again, it is non-volatile. Data is read optically instead of magnetically from a spinning disk using a laser. So, CD-ROM and DVD are the most popular forms, not as high as magnetic disk. Write one, read many, or worm optical disk used for archival storage when you want to store data. So, multiple write versions are also available. Reads and writes are slower than the magnetic disk. But then you have what is called as jukebox systems, where you have a large number of removable disks, a few drives, and a mechanism for automatically loading and unloading disks for storing large volumes of data, because one disk cannot accommodate the complete database, most databases. For example, you take a bank or things like that, the complete database cannot be credit card, for example, insurance, all that you cannot store in a single magnetic disk. So, you have what is called a jukebox. The advantage of jukebox is there are multiple disks, removable disks, and a number of drives, and you have a mechanism which will automatically load and unload disks for storing large amount of data. Another type of storage is the tape storage, which is non-volatile, again used primarily for backup, because it is much slower. So, it is used for archival data where you want redundant data to be stored, and it is a sequential access, and it is much slower than the disk. The advantage is it has got very high capacity, and tape can be removed from drive, and storage costs much cheaper than disk, but drives are expensive. Though the drive is expensive, the actual storage media is relatively cheap, and also like you had jukeboxes for magnetic disk, you also have tape jukeboxes. Next, talk about another important concept which we have actually covered, but depending as we already told you is the storage hierarchy. Now, as we have already told you, there are some parameters by which you judge a memory. One is of course whether it is volatile, non-volatile, one is the speed, one is the cost, and one is the how it recovers, how much power failure, how it affects, and so on. So, based on that, basically speed, we have defined what is called a storage hierarchy. So, this is a typical storage hierarchy where you have the most lowest one, that is a magnetic disk at the bottom of the hierarchy, then you have the optical disk, then you have the magnetic disk, then you have the flash memory, then you have the main memory, and then you have the cache. Now, why is this storage hierarchy very important for database managers? Because of this, flash memory, main memory, and cache are volatile. or at least main memory and cache are very volatile, but cache is faster than main memory. So, what is the most important depending on the queries and the type of access. For example, in a bank there are some customers who have transaction every day. So, maybe those type of data can be stored on the cache. So, depending on the emergency and the frequency of querying of that data block, those blocks, it is not the complete file, the blocks, which blocks are affected, those blocks can be stored in the cache. And depending on the importance and the time, and so the effectiveness of a database management system, how quickly it responds to your request very much depends on what type of data is stored where. So, this is the slowest, this is the fastest, this is the most cheapest, this is the costliest. Of course, this hierarchy and this cost time ratio is changing as time in today's environment, where the speed of the memory and the cost of the memory, where the speed is increasing rapidly, the cost is decreasing. So, that is also an issue to be considered. So, when we talk about storage hierarchy, we have the primary, the fastest media, which is but volatile, that is the cache and main memory. Then we have the secondary storage, which is next level in the hierarchy, which is non-volatile, it is moderately fast access time. It is also called as online storage. This is flash memory and magnetic disks. Tertiary storage, that is the lowest level in the hierarchy, it is non-volatile fine, but it has got slow access time, and it is also called as offline storage, example magnetic tape and optical storage. From this you can make out, from this hierarchy you can make out that what you want to access and operate on, you put it in the primary storage, which you generally want not to be lost, but at the same time you want to bring it back and forth, that is frequent usage, but you do not want it to be lost, then you store it in the secondary memory. And any redundant material that you want to store in to guard against system crash and flooding and physical problems, you store in tertiary. So, this is a magnetic hard disk mechanism which you have, where you have the rotation of the, this is the spindle which rotates, and you have the cylinder. Now, in the cylinder you have the platter and you have an arm, this is the read write arm assembly, this is the read write head that comes from that assembly. So, for each platter you have a read write head, and this is the rotation of the spindle, and inside this each disk you have a disk, and each disk you have a sector, and inside and associated with the you have a track, and associated with the track you have a sector. So, this is the track and this is the sector. So, you have a number of tracks and each track has a number of sectors. So, this is the operation of the magnetic hard disk. Now, why are we talking about this operation? This operation and understanding this is very important, because depending upon where the head is, now suppose you are accessing something here, for example, it will be faster than what when you are accessing here, or if you are accessing something away, then you this movement time is also necessary. So, if you understand these aspects, you will be able to make use of your storage and make get a faster access using these type of mechanism, which we will discuss in the next class. So, the magnetic disk has the following components. You have a read write head, which I showed you, positioned very close to the platter surface, it will almost touch it. It reads or writes magnetically encoded information, that is the function of the read write head. Then you have a surface of platter divided into circular tracks, and each platter you can have, it will have 50k to 100k tracks per platter on typical hard disk. This is can increase also, and each track is divided in turn into sectors, and each sector is typically 512 bytes, that also can change. Typical sectors per track, you will have 500 to 1000, 500 on the inner tracks and 1000 on the outer tracks. So, this is also a typical organization. And then if you want to read or write a sector, you have the disk arm swings to the position head on the right track, and the so first is the head movement. For example, you want the head to you have to position the head on the correct track, and then once you reach this track, the platter the spindle has to spin, so that the data is written onto the correct sector. So, you have the track and the spinning of the the head read write head movement and the sector spindle movement to find the correct sector as important time parameters when you look at reading or writing on a sector. So, the head disk assemblies, you have multiple disk platters on a single spindle, usually 1 to 5, and one head per platter mounted on a common arm. So, that also you saw. That is a virtual cylinder, actually links the ith track of all the platters. The advantage is if you store data on the ith track, then the read write head movement is reduced. If you want to access the first, it is already in that position, the track in the next platter already is in that position. Cylinder I is used to define that, consists of the ith track of all the platters. So, and then you have something called a disk controller. This interfaces between the computer system and the disk drive hardware and accepts high level commands to read or write a sector, and it initiates some actions like moving the disk arm to the right track and moving the spindle or rotating the spindle such that you reach the correct sector. The disk controller also has another job, that is it computes and attaches checksums to each sector to verify that the data has been read back correctly. If data is corrupted, with very high probability stored checksum would not match with the recomputed checksum, that is a high probability, sometimes it can. So, it ensures successful writing by reading back sector after writing it. So, it will write and then read it back and check the checksum, and it also does some remapping of bad sectors. This you would have seen, it will reorganize the bad sectors. So, this is a typical example of how you have a system bus and you have a number of disks here, and this is the disk controller which will manage each of the disks. And then you have a disk interface standard also. You have ATA, which is at adapter range of standards, and you have the SATA. When you are buying a computer, you would have looked at the SATA disk serial ATA, and then you have SCSI, that is small computer system interconnect range of standards, and you have several variants of each of these standards. Now, when we look at disk, what is the performance measure of these disks? One is the access time and one is the seek time. I have already been telling about this. The access time is the time it takes to for a read and write to be issued, and when the actual data transfer that is the access time, the complete access time. I have given a request for read and write, and when is it that I get the transfer, or at least the transfer begins. So, this is divided into seek time, the time it takes to reposition the arm on the correct track, and the average seek time is half the worst case seek time, and it is typically 4 to 5 milliseconds on typical disks. And then you have the rotational latency. This is the time you have reached the correct track, but you have to reach the correct sector. So, the time it takes for the sector to be accessed to appear under the particular read write head. So, average latency is half of the worst case latency. The access time consists of two parts, the seek time and the rotational latency. The seek time is the time for the read write head to position itself on the correct track, and the rotational latency is for the sector to reach that. So, the performance measures again are data transfer rate, the rate at which data can be retrieved or stored to the disk. So, this depends on the different standards, and they have got multiple disks also. Okay. And then you have, this is very important, this is the mean time to failure, which is called as MTTF, the average time the disk is expected to run continuously without any failure. This is typically 3 to 5 years, and the probability of failure of new disks is quite low. And it basically for a new disk it is 5 lakhs to 1 crore hours, but it decreases with age. Then we talk about optimization of disk block access. So, now we come back to what is a block. A block is a contiguous sequence of sectors from a single track. So, the data is transferred between disk and main memory in blocks, which we have already discussed. Typical block size is about 4 to 16 kilobytes. So, for the optimization of disk block access, the disk arm scheduling algorithms order pending access to track, so that the disk arm movement is minimized, because disk arm takes a long time. And you have something called an elevator algorithm. You move the disk arm in one direction from outer to inner tracks or vice versa, and process the next request in that direction till no more requests in that direction, then reverse direction and so on. So, this is what is called the elevator algorithm. You keep moving the disk arm in two directions. And another thing is the file organization. So, optimize block access time by organizing the blocks to correspond to the new data, to how the data will be accessed. So, store the blocks in the proper track and pointer sectors, so that, or cylinders as they are called. So, store related information on the same or nearby blocks or cylinders. File system attempt to allocate contiguous chunks of blocks, example 16 blocks to a file. And sometimes files may get fragmented over time. So, for example, if data is inserted or deleted from a file, or free blocks, we have already seen how it can be segmented. So, sequential access to fragmented file results in increased disk arm movement, because you will have lot of blocks. So, it is up to the to speed up the file access, you have utilities to perform defragmentation. Okay. So, non-volatile write buffer speed up disk writes by writing blocks to non-volatile RAM buffer memory to increase it. Database operation that require data to be safely stored before continuing must write to disk, and writes can be reordered to minimize disk movement. So, write it in such a way. So, then you have something called a log disk, which is for sequential log of block updates. You can also do what is called as journaling the file system by writing it into an NVRAM. In this lecture, we will discuss the different types of physical storage media, displaying the different aspects of storage hierarchy. So, I want you to discuss checkpoints with an example, take a set of concurrent transaction and try to explain, and then what are the different types of physical media available, and why for a database management system it is very important to explain or how storage hierarchy affects database management systems speed of operation, and how what are the different issues in the different levels of the storage hierarchy. So, thank you.